Have you ever wondered how a company seems to know exactly who to target with a new product? Well, I can tell you it's not magic. A lot of the time, it's a really powerful and actually surprisingly simple tool from the world of machine learning called a decision tree. So today, let's pull back the curtain and see exactly how they work. Okay, let's just dive right in with a classic example. I want you to imagine for a second that you're a marketing manager. Your big task is to figure out which of your customers are most likely to buy a brand new computer. I mean, where do you even start with a question like that? Well, you'd probably start with data, right? You might have a big table, something just like this one, that lists customers by their age, their income, whether or not they're student, their credit rating, and of course, the most important column, did they actually buy a computer or not? It's a whole lot of information to try and make sense of just by looking at it. But what if you could take all of that messy data and just transform it? Turn it into a super simple visual flowchart that practically hands you the answers on a silver platter. Well, that is exactly what a decision tree does. All right, so we've kind of set the stage here. Now let's really dig in and define what a decision tree actually is. At its absolute core, it's just a map of decisions. You can think of it like a game of 20 questions. The machine just keeps asking a series of questions about the data, splitting it into smaller and smaller groups until it can confidently predict an outcome. So each branch on the tree is a question, and each little leaf at the very end. That's your answer. Now, what's so brilliant about this is how easy it is for us humans to understand. We can literally follow the logic down the tree, which, trust me, is not something you can say for a lot of other machine learning methods out there. And here's the really cool part. We don't have to draw this tree ourselves. Nope, the machine actually learns how to build it, all from the data. So let's take a look at how that happens. Yeah, this is the big question, isn't it? How does an algorithm look at a flat table of data and figure out the most logical, most effective flowchart to predict something? What's the secret sauce here? Well, the answer is a process that has this kind of complicated sounding name, recursive partitioning. But honestly, the idea behind it is incredibly simple. The algorithm just splits the data over and over again. And with every single split, it's trying to make the new groups as similar or as pure as possible based on their outcomes. So we start right here with our full data set. We've got our 14 customers. Some of them bought a computer, some of them didn't. The machine's very first job is to find the single best question it can ask to split this one big group into more predictable, smaller groups. And the process looks pretty much like this. First, the algorithm picks a variable to test, let's say age. Then, it finds the best way to split the data using that variable. In our case, it could be 3 age brackets. Then, it actually measures how much clearer the picture gets after that split. And then, it just does it all over again on the new groups it just created. It's a loop. So let's actually walk through that first step together. The algorithm decides to test age as the very first question, and it splits all of our customers into 3 buckets: those who are 30 or younger, those between 31 and 40, and everyone over 40. And look at what happens. It's brilliant. Our one big kind of messy table is now 3 smaller, much more organized tables. You can already start to see some patterns emerging from just this one simple split. But how did the machine know that splitting by age was a good idea to begin with? Which brings us to a really key concept. How does the algorithm know which split is the best one? It's all about finding what we call the purest split. So what do we mean by pure in this context? Well, a group is perfectly pure if every single person in it has the exact same outcome. So for example, if we have a group with 5 customers and all 5 of them bought a computer, that group is 100% pure. And the algorithm is constantly hunting for these perfectly pure groups. Now check this out. Our 31 to 40 age group. Look at that. After we split by age, we stumbled upon a group where 100% of the people bought a computer. That is a perfectly pure node. The algorithm absolutely loves this. It's a dead end, a final answer. No more questions needed for these folks. But now, compare that to the group of customers who are 30 or younger. It's still pretty mixed, right? Some bought a computer, some didn't. In other words, it's impure. And this tells the algorithm, okay, my job isn't done here yet. It needs to keep asking more questions to try and split this group up even further. So how does a machine actually measure this impurity? Well, it uses a metric, and a really common one is called Gini impurity. The easiest way to think about it is just as a mix-up score. A score of 0 means perfect purity. No mix-up at all. So the algorithm's entire goal with every single split is to make the Gini score drop as much as it possibly can. So this basic principle, splitting data to reduce impurity, that's really the foundation for all decision trees. But, just like in nature, not all trees grow the same way, and that leads to a few different types you should know about. One of the biggest differences really just comes down to this. How many branches can a single decision have? Is it only allowed to ask a yes-no question that creates 2 branches? Or can it ask a more complex question that creates several branches all at once? And that brings us to the 2 main flavors. You've got CART, which is probably the most common. It likes to keep things simple, sticking to yes or no questions, which creates those binary 2-branch splits using the Gini score we just talked about. Then you've got CHAID. It's a little different. It can ask more complex questions that result in multiple branches at once, kind of like that age group split we saw earlier. And it's not just for yes or no type questions. There's a variation called a regression tree. It works in pretty much the same way, but instead of predicting a category, it predicts an actual number. So, for example, it could be used to predict the price of a house or how much a customer is likely to spend. Okay, so we have this beautiful, logical tree. It all makes sense. But how does that actually translate into something a business can use? How do we get from a diagram to an actual decision? And this, right here, is the payoff. Each path, from the very top of the tree all the way down to a final answer, it becomes a simple, readable rule. For instance, a rule from our tree might be, if a person's age is 30 or younger and they are a student, then it's very likely they will buy a computer. See? They become these clear, actionable instructions, which is honestly the biggest strength of this whole approach. So these intuitive, really powerful flowcharts, they're being used everywhere, from deciding who gets a credit card offer to even helping doctors with medical diagnoses. Their biggest advantage is that we can see exactly how they're making decisions. But that can also be a challenge, because if a tree gets too complex, it might just memorize the data instead of learning general patterns. Still, it really makes you wonder, right? As machines get better and better at growing these trees, what other crucial decisions are we already trusting them to make for us?